Okay, thank you for joining this STRIDE webinar on the utilization of connectivity and automation in support of transportation agencies' decision making. And this webinar is going to be on phase 1 of the project, which we just started phase 2 a few months ago. To continue with the activities on the project. So we have today a presentation that I'm going to present with Dr. Michael Hunter from Georgia Institute of Technology and Dr. Shoaib Samandar from North Carolina State University. We have with us that work with us is Dr. Lily from Alfredo from University of Florida, and Dr. Nagy Rafael from North Carolina State University, and Dr. Gwen from Georgia Institute of Technology, and several students from the universities. Basically, this project is funded by the STRIDE UTC, University Transportation Center, which is a regional center for the southeast of the United States. It has 10 universities, as you can, 10 universities. Basically focus on research, education, and technology transfer of research. So we're going to talk about some background on the project, which is focused on simulation of advanced technology vehicles, which can include connected, automated, cooperative vehicles. And then Dr. Michael Hunter will talk about the state of the practice based on the review of literature and also a stakeholder workshop that we had. I'll come back and talk about guidance for ATV modeling, and then Shoaib will talk about use cases of ATV modeling. A couple of them, we had several, but considering the time constraint, we're going to talk only about a couple of them quickly. So it's expected that traffic simulation will play a critical role in supporting the planning, design, operation, and management decisions of agencies, particularly that we don't expect that these technologies will be on the road for a long time, especially the more advanced feature of them and the cooperative features that have not really matured enough yet. So for this reason, simulation will play a major role at this point in time to make decision about the highway design and the planning and so on. The agency needs to prioritize their support, considering the limitation on the budget, and having a different type of technology on the road, and each one of those technology require different type of support. We need a simulation model that show the benefit of or the impact of those technologies, and the both in terms of positive effect and adverse effects if you don't provide that infrastructure support, both the physical infrastructure and the digital infrastructure. So the objectives is to assess the existing research, development, models, and methods that are available in the literature. We also, the other objective is to document the state agency needs regarding planning and operation with the presence of advanced technology vehicles. And we use ATV rather than CAV or CV here because we think that this is more inclusive term since there are so many different type of cooperation, automation, connectivity, and even electric vehicles and so on. So we use the ATV instead of the CAV. We also the other objective is the identification of modeling framework and guidance and demonstration of the use of simulation for use cases. Although this project focuses on simulation, it is recognized that the analysts need to have an integrated approach and thinking about all components of modeling that are needed, including how to model the supply, changes in the supply in terms of either policy or physical infrastructure or digital infrastructure, in terms of demand changes, which normally we need in that case advanced demand forecasting models and dynamic traffic assignment and all of these other things. And then performance changes, which we can do that using macro model or meso model or micro model. And finally, a network integration that combine all of these components. An important part of this is the identification of the technical approach. Considering that we are in the early stages of simulation, we have to be thinking about what is the best approach to simulate these vehicles, what is the best combination of tools that can and should be used. So there is no single tool that can provide all the functionality and all aspects of the CAV. Many of them do not exist. So many, even in the recent years when they started incorporating some of the CAV feature, the focus is more on specific things like dynamic merge or dynamic lane changing or CACC, but we realize that or cooperative adaptive cruise control CACC, but realize that there are many application of ATV or CAV that cannot be modeled. Consider the operation at the unsignalized intersection and accepting gaps in the traffic, or even a permissive left turn that's or red light violation warning or control of vehicles so that they don't hit the red or things like that. So all of these would require API type of modeling. In addition, the user may not be comfortable with the existing modules in the tools, and may introduce their own CACC models or their own lane changing models and so on. So a lot of time you would need interfaces, code written in API, or even a software that is interfaced with as a software in the loop or even hardware in the loop with the simulation environment. Another important aspect of modeling or simulation of ATV and simulation of ATV is the amount of uncertainties associated with this. So we don't know a lot of things about when does market penetration will be realized, and for different type of vehicles. You know, we have heterogeneous kind of traffic in terms of connectivity, automation, and cooperation, in addition to different modes and the top of that, and so on. So that will be an important uncertainty associated with this. Also, the algorithms themselves, both from the vehicle side and the infrastructure side, we don't know what the OEM's module will look like for a lot of these applications. We can assume, but on OEM1 may have totally different use of the data than OEM2, and we may not be able to really replicate all of this. But however, we have to accept something that kind of generic, that model all of represent this type of algorithm. The behavior of a human, both inside the ATV to set the parameters of car following, lane changing, and gap acceptance, and so on, in addition to the behavior of drivers and also other users of the roadway, like vulnerable road user around the ATV. Are they going to be more aggressive, or are they going to be more timid when they realize that the vehicle around them is an ATV vehicle? Private versus shared mobility, that's also going back to what we said about connecting it to advanced demand forecasting model that can estimate those. The impact, again, the impact on demands. Are people gonna, because of the ease of transportation, are gonna be more willing to use these vehicles, or are they gonna be less travel? So, Mike, are you there?
Yep. Do you hear me okay?
Yeah.
Fantastic. All right. So I'm just going to do some really quick literature review overview and talk about a focus group we did with a number of folks from the state DOTs. First slide, I have absolutely no intention of reading this to you. I know better than that. This is more just to be up there to let you see that there is a much more detailed literature review in the background. It is available as part of the report if you want to go dig into it. What we're really going to get into, what I'm going to get into right now, is intended to be much kind of a high level, a few of the bigger issues, particularly related to the modeling and simulation. That is the primary interest in this project. And also, I'll acknowledge right off that this literature review was done, probably over a year ago, which at this point, in AV makes it almost ancient. So, but I think it still gives us hopefully some good insights. So you can go to the next slide. So if we talk a little bit about, the freeway side of it, there was a lot of literature on freeways. That seems to be one of the primary areas of interest. We did certainly look at, there's analytical, macroscopic, different versions of models, but microscopic does seem to be when we start getting into a lot of this sort of the tool of choice, at least when they're trying to get kind of the detailed operational studies. And as we start getting into those, we certainly found, when you look at a lot of the studies, that the result is very dependent upon the assumptions. So I don't think that's a statement that nobody's heard before. We're not breaking some incredible ground there, but it is very important when you're looking at these studies to understand the importance of the assumptions that they're making. One of the most important tends to be the time gaps. So what are the gaps that are assumed between the vehicles, and vehicles of different types, maybe an AV, as a lead or lag with a human driven, or two AVs together, or CAV, or two CVs. Those assumptions really start to come into play in what the operational and safety results that come out of these models. We did find that it's still very typical for a lot of the CAV modeling to use a cooperative automated cruise control algorithm for the longitudinal control, where the magic tends to come in is going to be in the lane changing and the weaving, where you'll find each different paper, a lot of different research, handling how they're going to, handling it in a different manner, how they're going to deal with that. We also found you would see generally the results that it was said that in CAV introduction with V2V usually had a positive impact on capacity, although when the connectivity wasn't there, it would not be quite as uniform in the results you'd find in the field about whether or not you had those increases. One of the challenges, of course, is that the reviewed studies, they generally lack strong empirical evidence. There's just not a lot of field data, although there is some, and since this study has come out, there has been more. But that is one of the challenges, is finding the empirical evidence upon which to verify, calibrate, and validate people's models. So there's also a piece of that is the other version of this, which is well-designed studies to investigate driver behavior in the presence of the automated vehicle. So we're getting more and more information on the automated vehicle or the connected vehicle, but we also need to understand how those who are in the other vehicles in the traffic stream, assuming a mixed traffic stream, would be responded. You go to the next slide. We can think on the arterials, there's quite a bit of work looking at the idea of vehicle trajectory control and looking at how to optimize the individual intersections or potentially a corridor. And in that work, you tend to see a combination. Can you optimize trajectories and the signal control at the same time? You'll find work that looks at the individual trajectories. Maybe you could do some sort of platoon optimization, moving wheels together. So from a control theory point of view, there is a challenge still with a lot of this work, and then it does tend to be a bit more simplified. The phasings tend to be simplified, maybe not getting into permitted lefts or how to handle the turn movements and such. So as the work progresses and there's more work every day coming out, finding that complexity to better match the real world is becoming important. It's also not necessarily clear in some of the work exactly, again, how the human drivers are going to be reacting, and are we properly capturing the impact of human drivers in this field, in these studies. And there have been some field studies that have done a good job of illustrating how complex this is going to be when we get into it. There's some of the significant gaps does still seem to be tying the sensing abilities and communications required to make these systems work, and communicating with the infrastructure, communicating with the vehicles, and communicating if there's a driver, what's going to be involved there. Some of the gaps we noticed is the realism of some of the models in capturing really the capabilities and the various functions of the intersections. Looking at some of the methods that could be used to leverage CAV technologies. And one interesting challenge that we also, of course, notice is a lot of the simulation work is based on a simulation tool that the researcher themselves developed, which is fine. I mean, that can be great. But when we talk about what our DOTs are looking for and what our agencies are looking for, that becomes very difficult because they don't have the ability or expertise to work with those tools. So one of the challenges, of course, is moving from some of these custom tools to models or tools that the agencies are capable of familiar with. And again, that is occurring. And there's very limited field experiments. Could you go to the next slide, please? Safety. Well, there's a lot on safety. Safety is one of the driving forces behind CAV. We certainly, there's a ton of work out there on V2V and V2I and all the different variations of. I'm not going to read all these, but you can find work on almost all of these. There's been testing on a lot of these. So this is definitely a good topic. A lot of the work has been done there's also been work now done in driving simulators, there's field tests. A lot of this exists on cars that are being sold today. And then again, the microscopic traffic simulations, as we've talked about, is that seems to be sort of the place people like to go. And you'll see throughout the literature a lot of examples highlighting the benefits. Let's go to the next slide. But as we get a little deeper and we start thinking about sort of the CAV and the AV part of that, well, now there's not quite as much out there, and we start again getting into the assumption issues and the penetration issues that Mohammed was talking about earlier. And one of the ways people are trying to address this is through surrogate safety measures. Been around for a long time. We all have some familiarity with that. The idea, of course, combining the surrogate safety measures with a simulation modeling to allow essentially a simulated version of the surrogate safety. Surrogate safety, just at the highest level, we tend to be thinking about frequency, severity, and duration. That's what we're trying to essentially get a sense of crashes, right? What's the likelihood? What's the severity? How long? Some examples, time to collision, reaction time, deceleration rate. There's all, there's post-encroachment time. There's a long list of these. What we have found when you look at the literature is certainly that applications using connectivity are the research is stating that this can reduce response time, decreasing the conflict likelihood. It can also, as the market penetration increases, you'll see a decrease in speed variation, again, potentially reducing the likelihood of crashes. But we also did see there were studies out there that basically had conflicting results. We'd find some studies for, say, a low penetration rate, or maybe low AV penetration rate, that would say that might increase the number of crashes, and a study on the other side that, with the exact opposite, saying it decreases the number of crashes. So there clearly is a lot of unknown still. And again, this goes back to our earlier statement. A lot of this comes down to, what do you assume? What what do you assume about underlying parameters of the model? What do you assume about the different factors that Mohammed was talking about in terms of penetration rates, in terms of the algorithm itself driving the vehicles, on how people are going to interact with those vehicles? So that leads to this uncertainty, and then we kind of have to have a way to model these. One of the issues that then also starts to pop up is model calibration, and there is some discussion in our report about model calibration. But that really starts to become important, particularly when you don't have field data or you don't have significant field data sets. How does one calibrate? Now that is starting to change. There is a lack of open source data, although some data sets are starting to exist. I listed one example there that the team has been able to get hold of and is starting to look at. So to some degree, those data sets are starting to become available, but they are still very sparse. I think it's going to be some amount of time before we have a really good sense of that. Can you go to the next slide? So we did a survey, actually a focus group. We did an in-person focus group. It was November 2020. It was online with state DOTs, mostly within the southeastern United States. And we were focused on simulation modeling needs when it comes to AV, CAV technologies. The topics were broad. We want to talk about their efforts, their plans, their barriers, their challenge, really go through it all. Can you go to the next slide? Next slide. So for instance, this was a list of questions that we worked through, and it was more of a discussion, right? The idea was to put the question out and sort of have a discussion with the agencies, get the agencies discussing among themselves, to really try to understand the issues that the agencies are facing. For the participants from the agencies, we essentially reached out to each DOT and FHWA and sort of said, this is what we're trying to do, and look for those agencies to sort of recommend who would be the person to participate in that focus group. So you can see that we're looking for their activities. We're talking about their major issues and questions regarding adoption, performance metrics. What's their plan? Do they have a roadmap? What are they organizationally changing? How are they considering that? How are they modeling? Who is doing the modeling? What are the key questions and answers they're trying to get out of their models? What are their barriers? And of course, the collaborations is going to be an important part of both within department and also with organizations outside the department. So some of the quick takeaways, again, there's more in the final report, but if we can go to the next slide. Big picture, right? The highlight of the whole thing was there was definitely a strong tendency that the agencies were looking for. They had this need to provide a practical and realistic guidance for transport agencies to account for CAV impacts. There was certainly just a sense that they really didn't have at their hands practical tools that they could use, so realistic guidance. They were somewhat guessing in the dark. There was a great deal of uncertainty. They just didn't have a sense of what the impacts of these different technologies was going to be. They really want help to guide deployment and investment decisions. I found it very interesting to really hear the discussion and how much was talked about on this idea of return on investment, that they need to have a sense of what the ROI is, that the dollars are not infinite and there's competing dollars to do different things. So what is the return on investment of doing this? There's also quite a range across DOTs. Some are heavily invested, some are almost non-existent. They're sort of watching to see what others are going to do. So you really saw that range. Although there is significant progress. A number of the DOTs had implemented a number of test beds, and I think you could argue some were well beyond test bed with more of a widespread deployment. Let's go to the next slide. So a couple of the current developments, we had DOTs who have RSUs on urban arterials. They're looking at, they are deployed vehicle to everything applications on a broad scale. There are DOTs who have done test beds or deployed queue warnings, crash warnings, pedestrian collision systems, looking at rural settings, transit applications, preempt applications. So across the DOTs, there are a number of applications that are being piloted in test bed in the field. There was a discussion of integration with ATC, MTD initiatives. There are a number of state DOTs who are looking at multi-year CAV programs, so they were really making a broader push. And I also found it interesting to see how many brought up the AASHTO SPAT challenge. So that definitely was showing to have some success in encouraging and sort of spurring on agencies to address some of the connected vehicle. Again, but we did see this wide variety from agency to agency. Next slide. Some of the issues and concerns, more specifically, that we heard from them was, again, this idea of a lack of knowledge and guidelines regarding CAV technology and the anticipated impacts. There was certainly a great deal of uncertainty, as Mohammed mentioned, in the adoption. What's the adoption rates going to be? How should they be planning for that? What are the vehicle fleet types going to consider? What are the potential traffic travel behaviors? That just uncertainty throughout each aspect was very challenging. If they want to try to model, if they want to try to use some of their existing terms, what are the input parameters they should be considering? What, in 2030, what is the percent of AVs? And if you can tell me the percent of CAVs or AVs, how do I calibrate my model to handle that? They're also looking for guidance and examples. So give them some usable examples they could learn from and follow to help them in their decision-making process. Again, they came back with this concept of the value proposition. What is the return on investment to make these investments in this technology? Next slide. Performance metrics. There was some good discussion on the performance metrics. I think one of the issues that was interesting to hear was really comparing the technology, what improvement you would receive when you use this technology versus if you just use sort of a traditional improvements, or what's the marginal improvement of adding this technology to a traditional infrastructure system. And then also, how could you use this to maybe replace something that you would have done in a more traditional way? So those comparisons, and again, you can see that sort of tie back to this return on investment and understanding. They found it very important that they wanted to be assess both safety and mobility impacts. Although, interestingly, and I didn't put a specific bullet in, they said currently a lot of their deployments really aren't based on those assessments simply because they can't do it. I mean, a lot of the current deployments are based more on, we're going to try this, we're going to get out there, we're going to do the pilot test and see how this goes. They're not able to do these analyses ahead of time, but they want to do safety, mobility, impact analyses. They want to know how another interesting question was, of course, how the technology is going to integrate with the current approval processes, such as interchange modification and facility capacity addition. Right, there's a standard set of processes. You have your environmental impact statements, and you have all these reports and analysis that has to be done before you do these large modifications. How do they layer CAV into all that? And they also wanted to make sure that as they look at metrics and they think about cost, that we're also considering maintenance, that we don't want to lose what is the operations and maintenance cost of these technologies over time. Next slide. And then tools. This was certainly, I think maybe almost the biggest summary of it is they really didn't know what tools to use or how to do it. They just felt there was a lack of guidance in using tools to do this type of analysis. The type of things that would be considered, they were pretty much open to anything and trying anything: analytic tools, simulation models, custom-made spreadsheets, regional travel domain models, you name it, it was brought up. Currently, the agencies, a lot of that tends to be work using consultants or researchers to select the tools and then even potentially do the analysis. And also, I mean, they have a strong belief that the simulation modules have the potential to certainly quantify the impacts, but they're just not sure yet how to do it. And this comes back to the comment I jumped to before, that the projects are really not based on the operational evaluations currently, because they just aren't able to do it. So what they want to do is then be able to model the operational strategies to determine the mobility and safety impacts. Currently very, very limited. So that's sort of where they stand. I think that's actually my last slide. You go to the next slide. So that's sort of our update of what the agencies were thinking.
Thank you, Mike. So as Mike said, then one of the main needs of the agency that's specified was to have the guidance on how to use these tools and how to select the tool and the approach and so on. So a major part of our effort was to develop at least an initial guidance that can be used as a living document, updated as we have more information about ATV in general. What we did then is to start with the existing guidance from the FHWA. Many of you on the call are familiar with the FHWA Volume 3. This is the 2019 version that has basically 7 steps of simulation, starting from analysis, planning, and scoping, data collection, analysis, base model development, verification, and then calibration, and this is a mistake, calibration and validation, alternative analysis, and analysis documentation. So we just revisited each of these steps and inserted information that are specific to ATV. So for example, an analysis, planning, and scoping, we talk about the analysis dimensions and what are the approach for each dimension. By dimension here, we are talking about the level of the modeling or the component of the modeling. Does it include demand forecasting or the impact of the supply component, which the physical and digital infrastructure, and so on. Does it include dynamic traffic assignment, route choice? And then what is the approach to use that? How are we going to treat the uncertainty that we have been talking about up to this point? What are the performance measures? A lot of the performance measures that are used for regular traffic may be still applicable, but a lot of new measures are also important. For example, more and more that stability matrices and other vehicle level type of measures become important as we talk about the reduction in the oscillation and so on, and looking at safety measures as an important measure, and so on. And then analysis tool selection, data requirement and availability, identification of the verification, calibration, and validation methodology. So as we mentioned, there are approaches to modeling ATV, and we detailed that. So one option is to just adjust the existing model parameters through changing the parameters in the calibration process to reflect, for example, ACC and CACC, and that is something that was done for example, in the recent releases of some of those tools that consider the behavior of those vehicles. So for indecent, for example, the Weisman model and Transmodeler, the General Motor model has been fine-tuned. The parameters on them have been fine-tuned to reflect the car following behavior of the CCA-ACC, and same thing with lane changing, gap acceptance parameters, reduce the stochasticity somehow to account that the vehicles are going to be more uniform in accepting gaps and lane changing. Another option, if that is found to be not available for some of the application or not adequate for what we are doing, is to use new connected vehicle models that are internal to the model. This is approach followed to replicate the recent existing model and the modeling of the car following and merging operation. Or use new ATV model developed by other or creating new models within or integrated with the tool. Also, there's opportunity for using software and hardware in the loop as part of the simulation to replicate as much as possible the performance of these ATVs. We also have done, and this we actually did it after we produced the final report for phase 1. As I mentioned, we are working on phase 2. So we compared some of the existing tools and how they model different type of applications of ATV or features of ATV. And the HCM and the tools that have incorporated the HCM procedures has procedures to account for the impact of CACC, cooperative adaptive cruise control, and dynamic merge, and so on the capacity using capacity adjustment factors. And they have those for freeways, signalized intersection, and also for roundabouts. And you could, this is the table that we took from the HCM. But simulation models also introduced built-in models. For example, VSIM contains built-in functions that allow the user to model 3 driving behavior: cautious, normal, and all-knowing, based on data collected from the Coexist project. And when you look at them, the cautious driving is supposed to replicate automated, not connected vehicle, while the normal and the all-knowing, they are supposed to replicate the connected automated vehicle, with the all-knowing replicating more advanced feature of cooperation and automation. And what you found out that actually when we did the comparison between these tools, we found that the cautious driving is actually give you capacity that is lower than the capacity of human driving. And that is because people are becoming more cautious as they when they don't have connectivity. That's the cautious is supposed to reflect the autonomous vehicle somehow. The transmodeler simulates 3 different levels, and we compare of the Society of Automotive Engineer, and we compared actually the HCM with the Society of Automotive Engineer with transmodeler with VSIM, and we found that these tools produce totally, in a lot of aspects, different results. Although some of them, when you change the parameters, they can get closer and so on. So the conclusion is that one need to be careful when use existing tools and be sure that they produce compatible results. When you run, a lot of time people use highway capacity manual procedures or for screening of the alternative, and then they use the simulation model for more detailed analysis of the alternatives. But if the two models produce different results, then you will find out that the findings from the screening does not support what the detailed simulation is finding. So that's something that modelers have to be cautious about. Calibration and validation, additional calibration measures are needed, maybe at the trajectory level and so on, compared to the normal or human driven, which we used to use macroscopic measures rather than trajectory measures for long time. Although we have now also a recommendation to get more into the trajectory level calibration. The calibration should be done for different conditions, such as different congestion level, lighting, and adverse weather condition. When considering ATV, field data may not be available. In those cases, we need to depend on literature and information we get from technology developers. And then we always good to compare the results from our analysis, what was reported in the literature, to be sure that we are not producing results that are illogical because we assume something that is not. For example, if the literature say that the CACC or even the high capacity manual say that the CACC is producing a capacity improvement of 1.6, capacity modification factor was of 1.6, that means 60% increase in capacity. Then if our model tells us that the increase in capacity is 200% or 150%, there is something wrong in our assumptions there. Alternative analysis is also important. It should consider, depending on the objective and scope, should consider supply, demand impacts, and performance impacts. So, I should have said there, depending on the scope, an analysis must seek to gain the latest knowledge or sense regarding various ATV indicators, such that we can compare and try to get the best estimation of those indicators. And then sensitivity analysis is recommended for alternative analysis because of the large amount of uncertainty. So then you can do a risk analysis or sensitivity analysis, and then from those you would recommend then the best alternative, rather than depending on one run with one assumption. You need to have an assumption from distribution rather than one deterministic kind of assumption. And that could include the market penetration and also the performance of the ATV and accepting gaps and car following and so on. But the recommendation, if we're going to do sensitivity analysis, we should test the boundary conditions for each characteristics, and then while fixing the other one. Obviously, you could do more detailed analysis that include risk analysis, which with Monte Carlo simulation, but that require a lot of computational effort and so on. Next, I'm going to pass it to Shoaib to talk about a couple of case studies that we did in phase 1. Shoaib.
Thank you, Mohammed. The case studies that we did for this project can be divided into 3 major themes: arterial safety, mobility, and freeway mobility. Under arterial safety, the case studies that we investigated included red light violation warning, unsignalized intersection gap assist, and signalized intersection left turn gap assist. The freeway mobility case studies that we investigated included CAV operations and mixed traffic, where we have AVs, TVs, CVs, and CAVs. The second case study investigated the impact of a dedicated lane for freeway operations and the presence of AVs and CAVs. And the last one looked into optimizing operations at freeway weaving segments in the presence of ATVs. The arterial mobility case studies were 2, and they explored signal control optimization and evaluation of operations, environmental quality at interrupted flow facilities. As Mohammed mentioned, we won't be able to go through all of the 8 case studies that we did for this project. I'm just going to cover 2 of them here: the red light violation warning and the impact of dedicated CAV lanes. Can you go to the next slide, please? So the first case study capitalizes on the connectivity capabilities of ATVs and investigates its benefit related to red light violations. This slide provides an introduction to the concept of red light violation warning. Basically, you have these roadside equipment or roadside units that broadcast signal phasing messages that will be received by the vehicles. The vehicle onboard units will determine if a red light violation is going to occur. If that is found to occur, then the signal logic may extend the all-red phase to provide safe passage to the red light runner. Can you go to the next slide, please? So coming to the case study objectives and methods, the main objective of the red light violation warning was to assess the safety benefits of this technology. In order to do this, the team needed a baseline stopping probability at the start of yellow that could be used for calibration of the simulation model, and also using a robust method of quantifying the impact of red light violation warnings. For this, the team relied on surrogate safety measures. Moving on to the methodology part, this study was a simulation-based study. The team used VISM's COM API to implement the red light violation warning. The model parameters that impacted the probability of stopping were identified first, and then using the previous research, the baseline model was calibrated to match field stopping probability. Following these steps, the red light violation warning safety effects were evaluated using SSMs. Next slide, please. Coming to the summary results, this slide underscores the importance of proper calibration of the simulation model, and also it presents the results for the case study. As Mohammed mentioned, calibration of the simulation model is of utmost importance for simulating ATVs. The two graphics that we have in the left show probability of stopping at the onset of yellow from real world and simulated values. The two distributions that you see there in blue and red, those are two different distributions. One is from simulation and the other one is from the real world data that was collected. The leftmost figure shows the disparity between real world and simulation probabilities prior to the calibration. This figure shows there's a significant difference between the two distributions. The middle figure shows that the two distributions overlap after calibration. Again, that underscores the importance of the calibration step. The right figure shows the number of conflicts as a function of red light violation market penetration rate. Visual observations of the figure shows that as the traffic gets more homogeneous, the number of conflicts reduces, and also we can see that the high market penetration rate of equipped vehicles decreases the number of conflicts significantly. Can you go to the next slide, please? Changing gears to the second case study, which is assessing the effect of CAV dedicated lanes on freeway operations. As we expect, AVs and CAVs will impact mobility, safety, and the environment. And based on the literature and review of the literature, the impact is expected to be positive at high market penetration rates, and there's a consensus of the studies that have done and looked at this. But at low market penetration rates, however, there's no consensus, and majority of the case studies show that there's a negative impact on mobility and safety. Two factors could probably be the reason contributing to this disparity and the negative impact: interaction with unequipped vehicles and lack of platooning opportunities. A sensible solution would be to put these equipped vehicles and operate them in a dedicated lane. Next slide, please. Again, we conduct a simulation-based study to investigate the impact of the dedicated lane on freeway mobility. We simulated a real-world freeway facility that was located in Raleigh, North Carolina, in Sumo, which is an open-source simulation tool. The facility had 3 lanes in each direction, and the leftmost lane was dedicated to CAVs, while the right 2 lanes were used by other vehicle types. We had 4 vehicle types in the case study, including AVs, CAVs, TVs, and CVs as shown here. The longitudinal behavior of the 4 vehicle types were modeled differently. For AVs and CAVs, we used VLM-99. For TVs and CVs, I misspoke there, I'm sorry. For AVs, we used Zhao et al.'s model, and for CAVs, we used Zhao et al.'s and Malanas and Schledover's model. Next slide, please. Moving on to the scenarios investigated, this case study looked at different factors such as market penetration rate, ramp volume, demand levels, and access egress lengths and policies. The total number of scenarios were above 300 scenarios that we looked into. In terms of market penetration rate, we had 21 different scenarios that included a combination of AVs, CVs, TVs, and CAVs. On the ramp volume side, we looked at 3 different volumes, 5%, 15%, 25%. On the access and egress, we looked at 2 different policies, limited and unlimited. Can we go to the next slide? All right, this slide shows the findings of the freeway merge segment. The 2 heat maps that I have here show the throughput difference between base case and dedicated lane. The left heat map is for limited access. So in limited access, vehicles can enter and exit the dedicated lane at certain locations. And the right heat map is for unlimited access case, where vehicles can enter and exit the dedicated lane anywhere on the facility. Some observations that can be made from these 2 heat maps is that CAV improvement ranges between 20 and 60% of market penetration rate for both of the access and egress policies. We see minor benefits at low market penetration rates for the unlimited access case, which is on the right side. This is potentially because the CAVs are not using the dedicated lane and they're merging and using the general purpose lanes. And lastly, unlimited access is beneficial when the dedicated lane is close to the operating capacity, let's say between 40 and 60%. I haven't shown the results from other freeway segments and facilities, but we have seen similar observations for the diverge, weave, and basic freeway segments. Next slide, please. Looking into the impact of dedicated lane from the fundamental diagram, this slide shows 3 scenarios, 20, 40, and 60%. By this figure, each of those scenarios make up the different rows of the figure. The 3 columns show the fundamental diagram for the 3 lanes that we have for the facility. The right 2 lanes, as I mentioned, are 2 general purpose lanes, and the left column shows the dedicated lane for CAVs. Within each of the subplots, there are 4 different markers representing 2 ramp volumes and 2 access and egress policies. The red shows the unlimited access, egress, and 5% ramp volume. The orange dot shows the unlimited access with 15% ramp volume. The green one shows the limited access with 5% ramp volume. And the last one, which is the blue, shows the limited access with 15% ramp volume. Looking at the general purpose lanes fundamental diagram, the 2 columns on the right, we can see similar patterns that exist between the 2 lanes. We have more scatter at high CAV market penetration rates. It's just because you have more vehicles that are trying to merge to the dedicated lane that creates a lot of scatter. The general purpose lanes are also impacted by both ramp volume first and then access and egress policies. Looking and moving to the dedicated lane, the number 1 factor that affects the scatter of the fundamental diagram is found to be the policies regarding the access and egress of CAV vehicles using the dedicated lane. Also, the market penetration rate and ramp volume were found to be the important factors contributing to the scatter of the fundamental diagram. Summarizing the 2 case studies I presented here, they show that the introduction of connectivity and autonomy impact traffic operations. The red light violation warning case study underscored the importance of simulation calibration and found that market penetration rate is an important factor that benefits the red light violation warning. And on the CAV dedicated lane, we found that access policy, market penetration rate, and ramp volume are the driving factors in dedicating lanes for equipped vehicles or for ATV vehicles. That's all, I think. Mohammed, next slide, please.
Thank you, Shoaib. So we have a few minutes to answer questions. If you have a question, please either put it in the chat or raise your hand, and we'll try it. Meanwhile, we have a couple of slides, I think, on upcoming webinar so please remember to ask either in the chat or raise your hand if you have a question. The webinars are tomorrow. We have October 19 on impact and analysis of rider comfort in shared modes during the COVID-19 pandemic. On October 26 is smartphone-based incentive framework for dynamic network level traffic congestion management. On November 1st, there is a possibility that this one will be postponed. On November 3rd, we have deep learning on traffic state prediction. And I think that's on the, let me look at the chat. There is something in the question and answer, and there is something in the chat. So let me look at. So this is from Undine. She said that Undine that the November one will be moved to December 9, and there is just a comment on the question and answer. Any question on anything that we talked about today? You can even unmute yourself if you want, since we don't have many questions. If you just unmute yourself and ask if you have a question. Okay, I think we don't have questions. That means we did a good job. Ondine, do you have anything to say?
Sounds great. Thank you very much for a wonderful webinar with lots of great information. And we will send a recording of this webinar to everybody who registered. And we'll also send a link to the project website that includes links to the final report as well.
Thank you. Thank you, everybody, for joining us.
Thank you, everybody.